But at a few special points, like a half, the tail unwinds, the clocks interfere constructively, and we get a large resultant value.
If the angle is, 360 degrees divided by a whole number, you get some very particular behavior that's very predictable. Those are the angles at which this function, when you sum the primes, they actually go far from zero. And what happens at a random angle, and you just start adding the primes up, it keeps changing which way it's pointing, and the thing just bounces around.
So why is this happening? Well, let's look at when alpha equals a half. Here, what we're doing is multiplying each prime number in the exponent by a half. In other words, dividing each prime number by 2. So let's do this for each of the primes. In the first column, we'll write down how many times it can be divided by 2, and in the second column, we'll write down the remainder. So 2 divided by 2 equals 1, leaving a remainder of 0, so we've just made one full rotation. 3 divided by 2 is 1, but that leaves a remainder of 1, so it makes one full rotation and then a half rotation. 5 divided by 2 is 2 with a remainder of 1, so it makes 2 full rotations and then a half rotation more. Now, we don't really care about the first column because it doesn't matter how many full rotations a clock makes, we only care about where the arrow ends up, and that's fully determined by the remainder. It's just the remainder times alpha. So from now on, we'll just keep track of the remainders. And what we find is that all of the other remainders are equal to 1. So all clocks except the first one point the same way. This is because when we're dividing whole numbers by 2, there are only 2 possible remainders, 0 or 1. And since we're working with prime numbers, only 2 can have the remainder 0 because no other prime number is even. Therefore, all other primes must share the remainder 1. Meaning all those clocks end up making another half rotation, so they all point left and constructively interfere. A similar thing happens when alpha equals a third. Now each prime is divided by 3, so the possible remainders are 0, 1, or 2. Again, 3 is the only clock that has remainder 0, so that points right. But all the other primes follow a special pattern, a pattern that makes the entire circle method possible. The remaining primes distribute themselves roughly equally between remainders 1 and 2, which means all the remaining clocks are rotated 1/3 or 2/3 of the way around the circle. Since these clocks are pointing to the left, again we get constructive interference. And this pattern of constructive interference also occurs for other small rational fractions. But for non-rational numbers, you don't get these nicely restricted remainders, so the clocks are roughly distributed equally all over the circle, and you get destructive interference. Hardy and Littlewood realized they could use this. Imagine taking this plot of the magnitude of the resultant arrow and wrapping it around a circle. What they found is that the majority of the contributions come from very small regions of the circle, what they called the major arcs. The rest of the circle only adds minor contributions, so they called these the minor arcs. This allowed them to split up their calculation into 2 parts. The major arc part gives you the main term for how many ways you can write a number n as the sum of 3 primes, and the minor arcs just gives you an error term. They then showed that if the generalized Riemann hypothesis is true, then the main term grows faster than the error term. So eventually, for some large enough number, call it k, this value will always be larger than 1, and the weak Goldbach conjecture holds. But there are 2 problems with this approach. The first is that they assumed that a generalization of the Riemann hypothesis is true, which we don't know. And the second is that they didn't actually specify that number, k. I mean, how big of a number do you need to get to before you can guarantee that all numbers larger than that adhere to Goldbach's conjecture?
Then we've got to wait until 1937, when Russian mathematician Ivan Vinogradov proves the same as Hardy and Littlewood. But he did it without the generalized Riemann hypothesis. So, assumption free.
It's one thing to just assume the Riemann hypothesis and say, oh yeah, you can make some progress. But Vinogradov's like, no guys, you don't need the Riemann hypothesis. You can really prove this stuff.
But again, he gives some large enough number for which the weak Goldbach conjecture will hold, without specifying that number. And so it's very unsatisfying. Over the next 19 years, one of his students did get that satisfaction when he could specify that number. Do you want to have any guess as to what the number is?
10 to the 50, 10 to the 80, 10 to the 3,000? I don't know. I was guessing things that are far too low, probably.
Yeah. It's about 10 to the 6.8 million.
Wow.
It's huge. But then, from here on, people start working on his method more, and they all use the same techniques. In 1989, the number was brought down to 10 to the 43,000. Next, it dropped to 10 to the 7,194. And by 2002, it had dropped